is equal to f of x. All that these have are fixed points, and its flow along a line, so there can be, depending on the what degree of polynomial f of x is, there can be a set of fixed points, alternately stable, unstable. So you flow away from the unstable fixed point towards the stable fixed point, and if there is going to be a set of alternating stable and unstable fixed points, which stable fixed point are you going to go to? Well, you are going to go to the one where it's going to depend on where you put your initial condition. So, for example, if there is another unstable chap sitting over here, and I want to go to this fixed point, then the initial condition obviously has to lie between S and U on this side and between S and U on that side. So those initial conditions would be drawn to this stable fixed point. So stable fixed point does not automatically mean that wherever you start out you would end up over there. That can happen if that is the only stable fixed point in the world. For example, if you were talking about x dot equal to minus x equal to 0, the only stable fixed point wherever you start out, you would end up over there. But if you have a large number of them, then each has its domain of attraction and what is generally called a basin of attraction. So this fixed point is stable, will draw neighboring points to it, and which neighboring points? All those which lie between this unstable fixed point and that unstable fixed point. So that automatically defines the basin of attraction of this particular fixed point. In one dimension, it is trivial to understand what the basin of attraction is. In any other dimension, if I have a fixed point, getting the basin of attraction was completely non-trivial. So there is no algorithm which will tell you what the domain of attraction, basin of attraction is. So, so one-dimensional systems, therefore, are particularly simple. So this is what we were talking about, and this becomes a little more interesting if I have a parameter which can be adjusted also as a part of f of x. So if there is a parameter over here which you can play around with, then you have the additional feature that for every value of r, there would be a diagram of this kind, but as I change r, the diagram can change. And this is what happened in our first example that we took of this kind, where x dot was r of x, r times x minus x squared, and you had two fixed points, one at the origin and one at r. And for r positive, so if r is greater than 0, that's what this picture tells you. The other picture would be, I mean, it's still a fixed point at r, but r can be negative. That's when you have this picture over here. So the position of the other fixed point vis-a-vis the origin flips in the two places, r greater than 0 and r less than 0. And r greater than 0, the origin is an unstable fixed point, and you flow away towards this. Whereas if it is r less than 0, the origin is a stable fixed point, and initial conditions lying between minus r and infinity flow to the origin, and over here initial conditions lying between 0 and infinity flow to this fixed point over here. So if I look at the fixed point as a function of r, there are two fixed points. One is along the origin over here and the other along the 45-degree line over here. So r less than 0, this part is stable, and for r greater than 0, this one is stable. There is an exchange of stabilities at r equal to 0. So this change in the behavior, change in stability, change in number of fixed points, one calls that a bifurcation. And what one is looking at over here is what's called a transcritical bifurcation. So we'll go to the next example where x dot is now r of x minus x cubed. So if x squared is present, then of course, I mean, there would be behavior which is going to be somewhat of this kind. So if you want to look at a completely different kind of behavior, you look at, just ignore x squared and go to the next variety, which is x dot equal to rx minus x cubed. So x dot equal to rx minus x cubed, that's the next example one wants to talk about. And if r is less than 0, so r negative, you have only one fixed point. So x star is equal to 0. So that's the only fixed point for r negative. That is the real fixed point. The other two are complex. For r greater than 0, you have three fixed points. X star equal to 0 is always a fixed point, trivially so. And then you have plus minus square root of r. So for r greater than 0, it's x star equal to 0 and plus minus square root of r. If I plot that up, then there is always the origin, which is a fixed point, and then it is plus minus square root of r. So plus minus square root of r, look, it's an increasing function of r, but not very fast. So I mean sort of bending over beyond the straight line, I mean below the straight line, turns round, has this feature. So x dot, so these are the this parabola over here, which is r x star equal to plus minus square root of r, which is r equal to x squared. So that's what this looks like. So these are. And now what about the stability? So these are the fixed points. So r greater than 0, three fixed points, this and this. R less than 0, only over here. Stability, r less than 0, obviously this is stable. The f of x, f prime of x star is equal to r minus 3x star squared. So if x star is equal to 0, f prime is r. So r negative, it's a stable fixed point, so r negative origin is stable. R positive origin has become unstable, and x star equal to r. So x star equal to r is minus 2r over here, and so for r positive, these are stable fixed points. So this is stable, and this is also stable. So which was sort of inevitable. R less than 0, only one fixed point. r greater than 0, and this fixed point is stable. So wherever you start out on your axis, x-axis, you will end up at the origin. And over here, there are two additional fixed points over here and over here. This has become unstable, this is stable, and you flow to this fixed point. If you start over here, you flow. So there is this division at the left and right behave exactly similar, which is one which you could have guessed from x dot equal to rx minus x cube. You flip x to minus x, this remains unchanged. So the x positive and x negative are just images of each other. Whatever is happening on this side also has to happen on the left side, and that's exactly what you are seeing. You have a stable fixed point. So, all right, I mean, now there is again a bifurcation over here. So this at r equal to 0, so and x equal to 0, you have a bifurcation, x star equal to 0, r equal to 0. You have a bifurcation from one fixed point giving rise to three fixed points. Exactly at this point over here, the 0 has become a triple fixed point. All these sort of meet at 0. It was a double fixed point at this point over here. So it's now essentially three lines merging at three fixed point lines merging over here at x star equal to 0 and r equal to 0. And thereafter, as r becomes positive, you have this extra number of fixed points, and the stability has also changed. What was stable before has now become unstable, and this is it. So, all right, so what the name for this bifurcation is picturesque. This looks like a pitchfork. So, I mean, that is, it would look like a pitchfork if you sort of pitchfork rotated through 90 degrees. And so, this is what one calls a pitchfork bifurcation. What if I change the sign of x cubed? So suppose I talked about x dot equal to rx plus x cubed. So if it was x dot equal to rx plus x cubed, then the fixed point is x star equal to 0. That's always a fixed point. And now for r greater than 0, that's the only fixed point. But for r less than 0, there are two additional fixed points. Right? The other two fixed points are square root of minus r. Okay? So for r less than 0, you have two additional fixed points. So when I draw this picture of fixed points once again, so this is x star versus r. I have the origin, the x star equal to 0, the line x star equal to 0 is a fixed point always. And then for r less than 0, I have two other fixed points. So there are two other fixed points for r less than 0. So here is so x star r less than 0. What about the stability? X star equal to 0, stable. For r less than 0, unstable for r greater than 0. the f prime x star is, as before, r plus, now because of the sign change over here, r plus 3x star squared. And so x star square equal to minus r makes this, so x star equal to plus minus square root of minus r makes this f prime x star equal to minus 2r, and if r is less than 0, then this is positive, saying that these fixed points are unstable, which is exactly what you would need to have, because if this is going to be stable, the adjoining two fixed points have to be unstable. So this is unstable and this is unstable. So what has happened? What has happened is that if I vary my r, I have in this system still a stable fixed point at the origin. But the difference between this stable fixed point and this stable fixed point is that the basin of attraction has been reduced. Over here, wherever I started, I would land up over at this fixed point. But over here, I have to, it is only this part and this part which is going to flow to this fixed point. So I still have a stable fixed point at x star equal to 0, but only with a limited basin of attraction. So there is a bifurcation occurring over here as well. It is almost similar pictorially. This is quite similar, except that it is in reversed. So there was this pitchfork over here is rotated through 90 degrees. This same pitchfork rotated through minus 90 degrees, rotated the other way, gives me that pitchfork. So this is also a pitchfork bifurcation, but now you have to differentiate between this pitchfork and that pitchfork, and depending on if you are going to go in this direction, you are, alright, you go from R going to R negative to R positive. You call this by convention a forward pitchfork, and this, by that same token, a backward pitchfork. A better nomenclature is that what exactly has taken place over here. These things make sense only when I have a system in mind. And so far as this kind of dynamics goes, the system that, at least what I would have in mind is that it is the dynamics of magnetization, which is given by Am minus Bm cubed, where A is some number times T minus Tc, and B is temperature independent constant. So what we discussed yesterday was that, look, any dynamics which looks like x dot is equal to minus del V del x, whatever effects you put on this side you can always write as minus del V del x. 1D has this great easiness. And if I put a random force in addition to it, then the dynamics, if I choose the random force in a certain manner which satisfies what is called a fluctuation dissipation theorem, and so words so far as this course is concerned, but suppose that happens, then this will go to equilibrium distribution for x, which is given by e to the power minus v by kt, which any StatMech course would tell you is the equilibrium distribution. So my choice of f of t over here to satisfy the fluctuation dissipation theorem would take me to equilibrium. So now what does this whole, this dynamics over here, what is it? Reversing, if I have a equilibrium distribution which is like this, then reversing the argument, you can say that the dynamics of this x which appears over here is going to be a first order dynamics which looks like this. So what is this dynamics trying to tell you? Well, what exactly is this equilibrium distribution for the magnetization trying to tell you? What it's trying, if you recall the mean field theory of magnetization, then what is it that one is supposed to model? This is, I know that for t greater than Tc, I have a paramagnet. So the spontaneous magnetization, average magnetization of this system is going to be 0, and t less than Tc, there is spontaneous magnetization, and if the average magnetization, so average magnetization, if I denote by m, then it is, over here it has to be m equal to 0, over here it has to be m not equal to 0. So that's the picture of a phase transition, second order phase transition, where continuously as I change the, so if you look at this m as a function of temperature, it is, and this is your Tc, so it remains 0, and for t greater than Tc, and then rises continuously from 0, rises continuously from 0 at t equal to Tc. So that is what this magnetization does. And the mean field theory for this, I mean, how does one get it? Well, one says that there is free energy and f of m, which is like am squared over 2 plus bm4 over 4, where a is that a0 t minus Tc. So this free energy looks like, the free energy is the V that I have written over there. So for a greater than 0, B is always positive. If B were not positive, the equilibrium distribution would not, I mean, large m's would be more favored than small m's, and so infinite m would be the equilibrium state of the system. So B is always positive. Let's not, I mean, get into any question of sign of B. So B is, I could have just set it equal to 1, which is what one will do in a minute. So I could have said that b equal to 1. It's not really of interest. Interest is a because it changes sign, and this sign changes of paramount importance, because for a positive, this is what f looks like. So this is a greater than 0, and for a less than 0, this is what it looks like. So this is what it looks like for a less than 0, and so the favored state, which is the minimum, which is the favored state of the system, is m equal to 0 over here and m not equal to 0 over here. So that is the mean field theory of second order phase transitions. And now you say, all right, what if I were to look at the dynamics? The dynamics of this would have to be that suppose I make a change from equilibrium how would I come back to equilibrium? The answer is that it is m dot, the dynamics is going to be m dot equal to am minus b. That is, it has to be this dv dx, and v is now just the free energy over there. So it is, and there is going to be obviously something which we are going to ignore altogether in this course really, some noise, some additional noise. What is this noise all about? See, what happens in these systems in a real world is that the magnetization that we are talking about is an average magnetization. It is something which is there when you have average. We are talking about a large distance. I mean, on a long distance, you don't look at the small scale behavior of the system. You look at it over a largish scale, and you see that there is this mean magnetization M. But the small scale fluctuations are always there. So if I were to look at this a system at smaller and smaller scale, length scales, I would find that there are fluctuations over there, and those fluctuations act like a noise for this large scale system, and they are the ones without, they are the ones which are responsible for providing this noise over here. So this is how the system equilibrates back. That is, if I were to perturb the system from this equilibrium distribution in StatMech and ask why should it go back to the equilibrium distribution, the answer is that there are these short scale fluctuations. You need a noise to go back over there, and the noise is provided by the short length, short distance fluctuations. And this dynamics has a scale separation in it. This is what is happening on a largish length scale, and when you have to have a better view of it, you have to have the short wavelength fluctuations in there, and those over here are being represented as noise. But coming back to what we are interested in is a much simpler part of this, that the dynamics, the mean field dynamics, if I ignore the noise, would be given by m dot equal to am minus bm cubed. You are only looking at the relaxation of this magnetization and over a long length scale, which also essentially means a long time scale. So over a long time scale, the dynamics of this largely correlated regions showing a certain magnetization is going to behave in that fashion over here. And believe me, if this did not exist, studying things like this would only be good in a maths course and completely irrelevant in a physics course. So the fact that this is actually, I mean, these have a natural setting. The standard second order theory of phase transitions in the mean field limit does look like dynamics of this one-dimensional dynamics of one-dimensional dynamical system is the driving force behind these discussions. So, all right, it is this what you are trying to see, and as you said, that there is this change. The equilibrium, what we are calling fixed points, are actually the minimum of the v of x. So with every f of x that you write down over there, you could have written down f of x as minus dv dx, and the fixed points that we are talking about are actually the minima or extrema of that fixed point. If it is a local maximum, the fixed point is unstable. If it's a local minimum, the fixed point is stable. Yeah. So that's the picture. Yeah.
Sir, can it be shown for that in general case that ft drives the system towards equilibrium and not away from it? Can it be shown mathematically? Or
yeah. Right. Yeah. Sure. See, that is why the point is I would put restrictions. If you put restrictions on f which allow you to satisfy a fluctuation dissipation theorem, that is when you would be driven to. So fluctuation dissipation is the key. Very good. So, all right. But now comes the why drive. There is a purpose behind saying all this. That this is, as you said, that as you saw, that it's a second order transition that this describes. So what we have talked about over here is that here is for, this is like the R is like A, and A is changing sign as the temperature is changing sign. So this is your high temperature phase. This is T greater than Tc in that language, and here is T less than Tc in that language. And if I have the if I look at the dynamics, then what would have been in the statics the minima or maxima, local minima or maxima of the free energy are the fixed points of the dynamics, and for T less than Tc, the fixed points of the dynamics are the answers that you want, that is a state with a finite magnetization, and which is a state with a finite value of the fixed point. This evolution has occurred continuously. But the more common transition that you are familiar with, that is, for example, water becoming ice or steam becoming water, is not a transition of this kind. It happens all of a sudden. That is, there is a change in the density at the transition point. So, if the parameter for, obviously, for the water to vapor or water to ice transition is the density, and the density has a finite jump. Except when I am talking about van der Waals equation and near the critical point in a van der Waals equation, right? So that is when you have these PV things, where the isotherms generally look like this. That is the region where the first order transition from liquid to vapor is taking place, and then, I mean, the subsequent T1, T2 up to Tc, where this sort of disappears. And thereafter, I mean, the PV diagram is just like that of a gas. So there is a Tc where you are, this flat portion has essentially become zero, and this is a second order transition where you are making a transition from what? From a region where, this is a region where liquid and gas are in coexistence. Right? That is what happens during this. So the coexistence region is being diminished and gone to zero. So from a two-phase region to a one-phase region. That is what this transition is all about, and that is a second order transition. So, so what do you use over just as we used a magnetization over here, what you use over there as the analog of magnetization is the density difference between the liquid and gas phase. And so at the critical point, the liquid, this difference in density goes to zero. It remains zero above the critical point because it's a one-phase region, and then below the critical point, this density, there is a density difference which appears, and this density difference appears suddenly if I'm talking about a normal transition. If I'm talking about a transition at these very high pressures near the critical point, it appears continuously. So, but the more common variety in magnets, the normal thing that you see is second order transition. In liquid gas transition, to see a second order transition, you have to crank up the pressure to a rather high, well, Anyway, so but it also exists over there. But now comes the question that, well, all right, I mean, what do I have to say about this first order transition? So what I have been describing over here, the point is that there was this second order transition over here. I flipped the sign of this term and the second order transition disappeared. So maybe if I try to do some doctoring over here, maybe the first order transition can come into existence. So that is the motivation for the next part of the next study in the bifurcation business, which is, I will start from so I start from that x dot equal to Rx plus x cubed and put x minus x5 over here. So I keep the symmetry of x to minus x, but I have added a minus x5, which you can imagine will stabilize things. The problem with R greater over here was that the solutions just ran away. No fixed points. If I put a negative term, that is certainly going to be arrested. Yeah. So that's why let's look at the fixed point structure with this. So x equal to 0, x star equal to 0, this R is negative, and unstable if R is positive. So x star is equal to 0, and the other x star comes from x star to the power 4 minus x star square minus R equal to 0, so that x star square is equal to 1 plus minus square root of 1 plus 4R divided by 2. Okay. So those are the other two possible values of x star that I have. So let me look at R greater than 0. If it is R greater than 0, only one of this, only the positive sign makes sense. Because if I have the negative sign, then this x star square becomes negative, and therefore those don't give me real roots. So if I'm looking at R positive, then there is just one value of x star square, and therefore two possible values of x star plus and minus. Now, what is the value of that x star at R equal to 0? So I'm only working with the plus sign, mind you. So with the plus sign at R equal to 0, x star square is equal to 1. So x star is plus 1 or minus 1. So here in this picture over here, so this is plus 1 So here this is 1, and after that it increases with increasing r. Eventually x star goes like r to the power 1/4. So it looks something like this over here, and something like this over here. So those are the two fixed points for r greater than 0. And obviously this has to be a stable fixed point. This is unstable. So this has to be stable, and this also has to be stable. Yeah. Now what if r becomes negative? If r becomes negative, then I can have things going till r equal to -1/4. After r equal to -1/4, this one is totally gone. So I can come up to r equal to -1/4. That's my limit. Beyond that, there is going to be once again just one. At r equal to -1/4, x star is equal to half, which means x star can be 1/√2 plus minus. So at this r, the x star is over here, or over here. Okay. Good. Now take the plus sign over here, and you have to come to, so you are looking at 1 plus 1 minus something, and you are going to generate, alright, let's look at it this way. R equal to 0, I have already taken care of the top points, 1 plus. There are other two, which is x star equal to 0. So this also has x star equal to 0, which is sitting over here. So this also has to be a point on this curve, on this fixed point curve. So this is a point on the fixed point curve, this is a point on the fixed point curve. There is nothing beyond this, which is also a point over here, and therefore if you looked at this carefully, you would find that this becomes a turning point, which goes like that, and similarly the reflected thing over here, which has to go. Let's say I'm trying to draw x star squared, or x star equal to 1/√2, 1 plus square root of 1 plus 4r to the power half. So I'm trying to draw this curve. I know that I can come only up to r equal to -1/4 when x star becomes, so x star exists between r equal to 0 and r equal to 1/4. So this one over here is going to tell me that what this is going to be is that you start from here at r equal to 0, it is this 1 that I have got over here, and then r becomes negative, and so it drops down. And how far can it drop down? It can drop down to r equal to -1/4, which is what it does. So I've come up to this point. Now you draw x star equal to 1/√2, 1 minus square root of 1 plus 4r to the power half. that is at r equal to 0, it's equal to 0. And then it grows. Because now this is becoming smaller, but I have a negative sign. It grows and grows up to where? At r equal to minus 1/4, it's over here. So this is what it looks like. And there is the mirror image on the other side. Yeah. So stability, this is stable all the way through up to over here. Right? The origin is stable all the way up to r equal to 0. So this has to be unstable. And this has to be stable, so this remains stable all the way down up to here. And similarly, this remains stable all the way down up to here. Correct?
This dashed line is the x equal to 0 fixed point.
Now, the dashed means it's stable.
Yes, it's stable x equal to 0.
Huh.
R less than 0.
Huh.
And this other x equal to 0 point comes from the solution of this.
Yes, right. Yeah. So the x equal to 0 comes from this, also comes from the fact that x. Yes. Absolutely.